Okay, we're not having a final exam, but I am going to quickly teach Chapter 10, which is linear regression. All right, explanatory and response variable. Explanatory is like the x, response would be like the y, or this would be the dependent, the independent variable, and this would be the dependent variable. Y depends on x. X is explaining the response in y. Could be a drug, could be, how you're feeling on the drug. Positive, negative, and no association. Okay, if x is increasing as y is increasing, or as x is decreasing as y is decreasing, that's a positive association. Negative would be they're both doing the opposite, or they're inverses of each other. So x goes up, y goes down, or x goes down, y goes up. That would be negative. No association means just your points are everywhere. I mean, some graphs could have a positive and a negative association, like positive, then it goes negative from here to here, then it goes back to positive, so that's possible. Correlation. The correlation R measures the strength and direction of the linear relationship. This is the formula, but we're not going to use it because we have a calculator. So R is a value between -1 and 1. So -1, this would be perfect negative linear correlation. This would be perfect positive linear correlation. That means if x goes up 5, y goes up 5, or as x goes down 20, y goes down 20. It's a 1-to-1. Something like anywhere between maybe 0.8 to 0.9 is, they would say, strong. Or, maybe 0.9 to 0.99, that would be very strong. And then, I don't know, moderate. There is really no industry standard, but maybe 0.70 to 0.80, and then the rest is weak. Or R equals 0, that would be no correlation. Now, R does not guarantee a linear relationship. I could plot y equals x squared and find R, and that does not mean it's linear. In fact, I'm going to do that. So here, x squared, 1, 2, 3, 4, 5. 1, 4, 9, 16, 25. And then I'm going to hit stat. Let's see. Calc. Linear regression. Second L1, comma, second L2. Look at how strong R is. But if you go to hit, if you don't have R and R squared, you have to hit second catalog and then scroll down and turn diagnostics on. So if we want to make a scatter plot, second y equals, click it on and then click scatter. And then I hit zoom 9. Look at that. This is a curve relationship. So R squared equaling almost 1 doesn't tell me if it's linear. It helps though, but doesn't get the final say. And correlation does not imply causation, which means you can see one variable going up as another one's going up. Like this could be number of movies Nicolas Cage puts out a year, and this could be life expectancy. So you'd be like, so as Nicolas Cage's movies are going up, the life expectancy is going up, therefore Nick Cage caused this. No, that's not the case. There's actually a website, I can't think of the name, but it gives you like hysterical correlation causational stuff. I'm sure if you Google it, you could find it. And look at that, yeah. So this is perfect positive correlation. This is strong and it's positive. This is weak, strong negative, or perfect negative, strong negative, and none whatsoever. I mean, it's 0.45. That's useless. If you're hanging out with a bunch of R values and you're 0.45, you're out the door. Let's go to number 7, and we're going to put this in the calculator. So stat, edit. Everybody put this in. So if we go to stat, calc, lin regression, second L1 comma second L2, we get this. So I'm just going to copy this down. So y hat is a x plus b, r squared is 0.82, r is negative 0.91, just so I have it here. Draw and label the x-axis. Well, that shouldn't be too hard to do. Plot each ordered pair. All right, well, we're going to be making a scatter plot. So, the x's are going up to 30, so I want, maybe 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. And the y's are going up to 15, so maybe go by 2s. 2, 4, 6, 8, 10. And then all you're going to do is plot them. So 1, 12 and a half. I don't know, do your best. 10, 8.7. 5, 14.6. You get the idea. But if you hit second y equals, and then hit zoom 9, there's the graph there. So then, you could finish it. Does there appear to be a linear correlation? Well, yes, there does, because the graph looks somewhat linear, and my R is strong negative. So yes, because R is negative 0.91, so that's strong negative correlation, and the graph appears to be linear. So interpret the correlation coefficient. Well, you would just say there appears to be a strong negative linear correlation between x and y. Okay, so we're gonna skip this. We're going to go to number 11. So we're gonna put this in our calculator. Let's hope I don't screw it up. 5890, 5340, 6500, 4800, 5940. Okay, so now we're gonna hit stat test, go to the very bottom, we're gonna hit lin regression t-test. Stat test, lin regression t-test. So L1, L2. All right, now, so we're gonna have to do our ho and our ha. So can you conclude there is a significant linear correlation? Okay, so that would be this. So you would say B equals 0 and B is not 0. So this is a slope. B is going to be the slope. So no slope, if a line has no slope, or no, I'm sorry, zero slope, it looks like this. So that's basically no correlation. This one's saying that there is correlation as long as the slope is something other than zero. We're not going to be doing this, so we just cross that one out. All right, so then my t-test stat, well, it's this formula. So what it is it's the, all right, here, so let's finish this. So that's going to be not equal to, and then we're going to calculate. So that S of B is the standard deviation of the residuals. Then it's divided by the standard deviation of X times the square root of n minus 2. So we're not going to get into that. All we have to know is that value is this value is 7.9. All right. I am going to write down the line of best fit, though. That's y equals, well, now this one, it's a plus bx, so just be careful. So a, negative 4.1, plus b, 0.001, x. So that's the line of best fit. And our p-value, there's our r, and there's our r squared, 0.1232. The p-value you can find the same way. It's just a t-CDF, or positive 7.9, comma 99, comma 1, 2, 3, 4, 5, 6, 7, 8. N is 8, so it's n minus 2. Right here, oh, it's a 2-tail, so you got to do 2 times it. And if you do that, you end up with that same p-value. So basically, since p-value is less than alpha, we reject HO. So there appears to be a linear correlation. Well, really with B it should be linear relationship, but that's okay for right now, correlation. And the correlation, it kind of appears to be positive as X goes up, Y's going up, but that's so weak, but okay, there you have it. Oh, and if we do look at the scatter plot, yeah, there appears to be a correlation. So this picture, based on our p-value, almost verifies it. Okay, we're going to go to number 16. Actually, let's do one more p-value. Let's do this one. Let's do 14. Right in the calculator. That's X, that's Y. If they don't tell you what X and Y is, then you have to kind of use common sense. Anyways, data's in here. Stat, test, linear regression, t-test. All right, now the HO and the HA, let's look at it. Determine if there is a linear relationship, so it's 0, not 0. If it's at a positive linear, like if it's at a positive linear, then you want your B to be this way. Negative linear, B goes the other way. We're not going to do that in this course, but if it said prove there's a perfect relationship, we would use ones here. And then calculate. So our test statistic is 1.7. Our p-value is 0.15. Our line of best fit is A plus B X. And since the p is greater than alpha, we fail to reject HO. So there's no evidence to say there exists a linear relationship. I'm keeping HO. Remember, B equals 0, that means no linear association. No linear relationship. Okay? Not doing critical values. And we're going to do 16. Let's put this in the calculator. Perfect. Let's see what happened. 896, 60, 820, 50, 771, 50, 696. Oh no, I forgot. 692. Shoot. Okay, so stat test linear regression t-test. Okay, so line of best fit is this 0.47 plus 0.07x. R squared is 0.76, R is 0.87, S 5.12. S is the standard deviation of the residuals. Okay, find the LSRL. We got that here. Slope, interpret the slope. So this means for each one x increase, the predicted y increases 0.07. So for each 1 foot increase in the number of stories, for each 1 foot height increase, the number of stories is going up 0.07. So that's what you do. You just put a 1 over and say for each x increase, for each x increase of 1, the y's do this. So if it was negative, you'd say it would go down 0.07. Interpret the y-intercept. So for an x equals 0, a building with 0 height, there are 0.47, the y-intercept when x is 0, stories, which doesn't make any sense. Usually the y-intercept doesn't make any sense because it's extrapolating the data. Your x's are only good between the lowest number and the highest number in the x's. X equals 0 is not in this range, so it's no guarantee. Find the predicted value for 800 feet. So to find the predicted value for 800 feet, I plug 800 into that equation that I found. This equation predicts my y for any x value. And now I know you guys have done this in Math 1R and Math 2R, but so that's why it should be coming back to you right now. But if it doesn't, read the textbook. The textbook is very resourceful. Well, all right, let's plug in 800. 0.47 plus 0.07. 56.47. Predicted value for 750. Once again, you plug this in. 24/7 plus. All right, because I don't have values for 800 and 750, but I can use the line to help me figure it out. All right, because this is what the plot looks like. And if I were to graph this line, 0.47, that's the best a calculator can do. All right, that's enough.